So in this video, I'm going to talk about statistical power analysis and how we use a power analysis to estimate sample size in the research design phase or to analyze statistical power after data has been collected. And I'll show you an example in GPower. So I've talked in previous video about hypothesis-driven research, where we collect data from a sample of participants, say 10 subjects, 20 subjects, and we hope that the results represent what the population is doing, the population of runners or students, whatever target population that you're interested in studying. According to these hypothesis designs that will ultimately determine the statistical analysis to test these hypotheses, whether it's looking at two groups using a t-test, or multiple groups using a ANOVA, or doing a randomized control trial using a two-way mix ANOVA, etc., etc. And so I've got separate videos for that discuss those in depth, but ultimately we come up with a p-value, right? It gives us the probability of error, it gives us the probability of observing a certain result given that the null hypothesis is true. It's like, how rare is the observation, the observed result that we have in our study if the null hypothesis was true. It's called the probability of error because it gives the likelihood of us committing a type 1 error, or us committing what's called a false positive, when we're saying that there is a difference between groups when in reality there isn't. And if that probability or likelihood is low enough, in this case less than 5%, we have enough evidence to reject that null hypothesis. 0.05 is the convention that's typically set for our field in kinesiology, sports sciences, but there are some instances in which perhaps you might set that alpha level 0.01 if you're dealing with something that has life or death implications, for example. Anyway, again, that is a bit of an aside, and then I saved that for another video. So statistical power is related to alpha level and this whole concept of null hypothesis significant testing. Remember, we're trying to determine whether we can extend the results of our sample to the population. And let's just say, this is an example I used in a previous video on statistical inference, where I'm comparing running times between running with cushioning versus stability shoes. And the difference in mean mile times are compared between both groups. I have a sample of 20 subjects, and let's just assume that the null hypothesis effect is a mean difference of 0. So if I run a study, and I found that the mean difference is roughly 1.1. Then I run the study again, it was actually closer to 0, and I run it again, it was actually negative 1.5, that means stability shoe is faster. And then I run the study multiple times, and theoretically I could run the study infinite number of times, again theoretically, and that sample, that distribution of random sample eventually is going to resemble a normal distribution curve, a bell-shaped curve such as this, whereas the middle of that curve, that central value, represents in this case the null hypothesis of the mean difference of 0. So this gives us an idea of the likelihood of committing a type 1 error, or, and I'll go here a sec, a type 2 error. So in this example, we had a sample of 20 subjects. So the critical t-value, that is the value above which a certain result would be deemed not a part of the null hypothesis if we assume a significance level of 0.05. So this here is our alpha rate. That is the rejection region. That's where it's safe for us to reject the null hypothesis. When we get a t-value, or a t-score, remember a t-score is a standardized score for, this case, a mean difference in units of standard deviation, or units of standard error in this case, because we're looking at a statistic here. So that alpha region is the probability of committing a type 1 error where it's low enough, in this case under 0.05, where we can safely reject the null hypothesis. This is under the assumption that the null hypothesis is true in the population, that a mean difference is 0 between shoes. Now let's say, for example, I repeated the study and repeated it multiple times, and this time the alternative hypothesis is true, where there is a mean difference, non-zero mean difference between running shoes. And you could see here that the two distributions are both normal and they overlap. So what we want to know, how far apart are these two distributions where we can confidently say that these shoes are statistically significant? Well, before we go into statistical power, we needed to define that type 2 error that I talked about earlier. And if we assume that the alternative hypothesis is true in the population, then the probability of us committing a type 2 error or a false negative when you're saying that there is no difference between shoes, but in reality there is, that's given by this beta region, this beta. And you can see the farther away it is from that value, that t value, if the alternative hypothesis was true, goes down the further away. So that's the beta region. That is the false negative region. So 1 minus that beta is known as statistical power. And statistical power gives us the probability of correctly rejecting the null hypothesis when it is false. In other words, it is the likelihood of us finding an effect that is statistically significant. And that statistical power is dependent on the alpha level, which we set at 0.05. It's dependent on the effect size. It's just the, how far apart are the results, in this case the mean difference between shoes. Directionality, whether we are interested in a directional hypothesis, we say that one shoe is faster than the other, or a two-tail direction. In this case, a non-directional hypothesis, where we're saying, we just know that they're different. We want to know whether or not they're different. So this is important when we go into G-Power and actually run the power analysis. It's also dependent on sample size. And if you go back to the theory and some of the basic concepts behind statistical significance testing, these random sampling distribution is dependent on the standard error. Right? Standard error is the standard deviation of this statistic, which is the mean difference. And this case is given by this formula. I'm not going to go over the details of how this mathematically derived. Just trust me, it is dependent on the standard deviation of each of the samples as well as the sample size. So the greater the sample size, the smaller the standard error is. The smaller that error is in sampling these mean differences from the population. So if we were to get a sample mean difference that is representative of the alternative hypothesis, for example, we can be confident if we have a high enough sample size that is precise, that is indicative of what, or more confident that is indicative of what the value would be if the alternative hypothesis were true. Cool. So it's statistical power is based on alpha level, effect size, directionality, and sample size. So there are a couple ways that we use a statistical power analysis. The most common way is in the research design phase, I would say right before, but before you collect data or even recruit subjects. It's called a priori estimation of sample size, given an alpha level 0.05. A statistical power, and typically that's set at 80%. The effect size, which we determine from previous data published in the literature or from pilot studies, and allows us to calculate sample size for quantitative research. Another use of statistical power analysis is to actually calculate the power after you've collected data. So let's just say you were, I can only you're limited on collecting data on 10 subjects per group for whatever reason, due to time, due to COVID, due to money, right? Due to funding. So then what you could do is collect the data and run your stats, your t-tests, your ANOVAs, and also run a statistical power analysis to determine, okay, how powerful are these results? Right, given an alpha level 0.05, the sample size that you included in your study, as well as the effect size. But the most common way, the proper etiquette in terms of research, is in the design phase and estimating sample size given alpha, power, and effect size. So the steps that are typically used in estimating sample size using statistical power analysis is you have to establish what you know about your research question, your research hypothesis. So you have to look in the literature, and I suggest, if it's available, systematic reviews and meta-analysis, and you're going to get an idea of what is meaningful in terms of differences between groups, or the correlation between variables, or if nothing's available, because I assume that you're looking into a research question that hasn't been answered before, you can do a pilot study. And the whole idea is to develop or estimate an effect size so you can subsequently calculate the sample size. Formulate your null and alternative hypotheses. I think by now you are familiar and comfortable in defining what those are in the context of your research question and or hypothesis. Decide on the appropriate statistical tests to test these research hypothesis. If you're comparing two groups in mean mile times, you use a t-test. If you're comparing multiple groups, you use an ANOVA. If you're comparing the same group that is pre, mid, post, you do repeated measures of ANOVA. So anyway, I've got a separate video for that discuss the statistical tests that are appropriate for the research question or hypothesis in mind. So just make sure that you decide on the appropriate statistical test, because that determines the type of statistical power analysis that needs to be performed. Specify the alpha level, conventionally set at 0.05 for our field of kinesiology, sports science, exercise phys. The desired test power, research has shown we want this 4 times the level of alpha level. I've seen it at 0.80, 80% is the typical level, but sometimes they'll increase that to 90% or 95%. So I like to start with 0.80, and that's what we're going to use for our example here in a few minutes. And then use all of that information to compute your required sample size. Remember, this answers the questions of how many subjects is needed in order to detect a significant effect with a probability of, in this case, 80%. Or 90%, whatever set power that you wish to detect these changes. Cool. So what about effect size? If you've taken evidence-based practice or athletic training, where we talk about some of the research methods associated with these types of study, most commonly used measure of meaningfulness or strength is effect size. And depending on the statistical analysis, the effect size themselves are measured in a number of different ways. Probably the more common and I guess relatively easier way to calculate effect size when you're looking at group means, the differences in say two groups, is using Cohen's d or Hedges g. In fact, that's what we're going to use today in this video. Or if you're looking at the relationship or association between variables, you want to look at the percentage or proportion of variance that's shared by those variants as indicated by the coefficient of determination, the partial eta square, the omega square. If you're looking at nominal variables, such as clinical measures of association, there are things like relative risk, odds ratios, sensitivity, specificity, kappa, and again, I have a separate video just for those types of nominal variables. So the effect size that we're going to do today in G-Power is a simple Cohen's d for an independent t-test comparing the differences in means between two groups, and it's given by this simple straightforward formula here, where it's mean 2 minus mean 1 divided by the standard deviation. Sometimes the standard deviation could be a reported standard deviation in the literature, such as a systematic review or a meta-analysis, or it could be a pooled, what's called a pooled standard deviation. You take both the standard deviations and you pull them into one there. Calculate that. You use existing data to estimate these means and standard deviation, as I mentioned earlier, from current research or from a pilot study if you can't find it in the literature. Now, the effect sizes, these are just some guidelines on what's considered to be small, 0.2, medium effect size is 0.5, then medium to large is 0.5 to 0.8, and anything above 0.8 is a large effect size. You could actually go above 1, and it just means that you have a higher probability of detecting an effect of that size. So make sure you choose an effect size that's realistic, that's representative of your research question, and perhaps most importantly, that it is clinically meaningful. Okay. All right, so we are going to use a tool called G-Power. Keep in mind there are a number of different software tools that allow you to run these statistical power analysis. I like G-Power. It's free. One, it's free, and number two, it's pretty straightforward to use. If you're taking my research methods course or my undergrad stats course, I have G-Power up available on Canvas for you to download. All right, so let's go ahead and take a look at an example in G-Power. So this is an a priori estimation of sample size. We have a clinical dietitian who wants to compare two different diets, A and B, in diabetic patients. She randomly assigns these patients to one of two diets, and at the end of the experiment the fasting blood glucose test was conducted, and she expects that there will be an average difference in blood glucose measure will be about 10 milligrams per deciliter. And she assumes as a standard deviation of blood glucose distribution to be 15 and 17 for A and B respectively. So given all of this information, we're going to use G-Power to calculate sample size. So let's take a look. Okay, so I've got G-Power. If you haven't already, download the latest and greatest from their website. Again, it's free of charge and really simple to use. So in this example, we're running a t-test, an independent t-test. So we're going to use t-test here under the test family. The statistical test is a difference in means between two independent groups. Means difference between independent groups. The type of power analysis, again, we're trying to compute sample size, so this is a priori. And in a different example here, I'll show you how to do post hoc, but for this one, for this case, we're trying to calculate sample size. Okay, is it one tail or t-tail? In other words, is our hypothesis directional or non-directional? In this case, I want to know whether or not there's a difference. And the dietitian believes there's going to be a difference of 10 milligrams per deciliter in blood glucose concentration, but she didn't mention whether the diet A or B would be greater. So she's just looking at a non-directional hypothesis here. So we choose two-tail. Let's set our alpha at 0.05, our power at 80% or 0.80. This allocation ratio simply means that you want to have even number of participants in each of the diet groups. Now effect size, let's go ahead and calculate this by hand. I'm going to go to determine, and she mentioned in this example that the mean group was, let's say, actually no, let's just say 0, because her hypothesis that the difference is 10, so it doesn't matter whether we put the 10, we're just looking at the mean difference. The standard deviation in one group was 15 and the other one was 10. Good. So go ahead and calculate the effect size and calculate, transfer to the main window here. So the effect size is 0.784, alpha level of 0.05, statistical power at 80%, and allocation of 1. Hit calculate. You can see here this is the similar t distribution or sampling distribution I showed you earlier, because we're interested in a two-tail non-directional hypothesis test. So you can see it split it up at a critical value of 2.0. This is the alpha, 0.05 divided by 2, so we got 2.5% on each tail. This is the alternative hypothesis. So this area right here is statistical power. So if we wanted 80% statistical power, we need a sample size of 54, 27 in each group. And you could see here a summary of the power analysis for a t-test. And you know, if you're taking my research methods class, what you do is that you would copy this and paste it onto the discussion board, and to illustrate, okay, this is your sample size that you need. Now let's just say that she was interested in she was interested in finding the number of subjects needed in order to find a significant difference between both diets at a probability level or at a statistical power of 90%. Let's take a look here. That sample size now has jumped up to 72, meaning 36 in each group. So again, depending on your situation, your clinical question, your research question, I would start it off at 80%, and then you could, increase it from there. Okay, so let's just say, for example, that I was limited or this dietitian was limited in terms of participant recruitment. She was only able to recruit 20 subjects or 20 patients for her study. So she performed the study. She found that the average difference between diets A and B was 12 milligrams per deciliter. Standard deviations were 10 and 15 for A and B respectively. Now we're going to use G-Power to calculate the statistical power given these results at an alpha level of 0.05. So let's go ahead and go back into G-Power and run that analysis. Okay, so let's now run a post hoc power analysis. Again, you would run a post hoc power analysis if you're interested in calculating the statistical power on data that's already been collected, whether it's you as a researcher that collected data or data that's already published in the current literature. So let's go ahead and run this t-test power analysis. It's the same research design, except we have data collected. Doing t-test, differences between two independent means, that mean differences between two independent groups. We're doing a post hoc because we're trying to calculate statistical power given the alpha level, sample size, and effect size. We're doing two-tail. We just simply want to know whether or not there's a difference between groups. I'll come back to effect size here in a sec. The sample size was 10 in each group, right? A total of 20. The alpha level 0.05. The effect size, in this case, she found that there was a difference of 12 between groups. Standard deviation was 10 in one group and 15 in the other group. And it really doesn't matter where you call group 1 or 2. Remember, this is a non-directional hypothesis. We just simply want to know whether or not there's a difference, right? Or, I'm sorry, we want to know what the probability would be, or the statistical power would be, in detecting a statistical significant difference. Oops, I forgot to do that. I'm sorry. That would be 0, 12, 10, and 15. Hit calculate. That is the effect size. That's a pretty large effect size there, 0.94. With a sample size of 10, that's the caveat there. We'll go ahead and calculate the statistical power, and you'll see here that it is pretty low. Only 51%. Even though the effect size is relatively large, because of the sample size being at only 10, the statistical power is 0. That means there's only a 50% probability of finding a statistical significant difference between groups. And if you go back to my lecture on the sample size part, because sample size determines the standard error, in this case it's only 10, so that means the standard error is going to be larger. There's a larger error in sampling, randomly sampling the data from the population. That in turn brought down first of all, it in turn increased the type 2 error rate and subsequently decreased the statistical power, in this case 50%.